Hello everyone, today my topic is CNN interpretability. My name is Wang. I come from Department of Biomedical Engineering. So I will introduce my topic from these two sections, background, including definition and motivation of interpretability. The second part is the method. First of all, what is interpretability? From Final and Bean's word, interpretability is the ability to provide explanations in understandable terms to a human. In other words, that means that we need to use human language, or at least the things that human can understand, to describe how the neural network works inside. Then, why we need to study the interpretability of the model? The first part is neural network is still a black box. If we could solve the theory behind the neural network or inside the CNN, we can do the following things. The first thing is we can learn by fewer data samples. Because if we could learn how a neural network works inside, we could know which kind of data the neural network really wants. In this way, we can feed those kind of data to the network, and that will reduce the data sets a lot. The second thing is that we can apply on high-risk application. As we all know that AI for healthcare nowadays only stop at the stage of assisting doctor, because the patients still don't trust what machine generates. The last thing is that we can develop a better model with the interpretability. So now let's introduce some typical methods to do the interpretability of CNN. The first group of methods called gradient-based method. The motivation is that since we input the image into the convolutional layer, the resolution and the feature space has already changed a lot, and if we want to visualize the high-level layer, hidden layer, we need to recover it into the input pixel space. So a group of people introduced a method called deconvolution net. So here's the thing. If we input image into a forward pass and we will get a feature map in the hidden layer, then we put this feature map into the deconvolution net, and we will get the reconstructed image. As we can see here, the performance show that in a higher level hidden layer, actually the model tends to learn more information about the object or the semantic level things. These are more performance figures. As we can see here, in a in higher level, we can learn a lot of semantic level information, but in the shallow layer, we can only learn some texture information. But this kind of method also has some limitation. It will generate some noise in some hard cases. For example, this one is the hidden layer visualization, but we can see the outlier of the dog and the cat, but there's so many noises that avoids to make it clear. Then a group of people introduced another method called the guided back propagation, and in this method, it adds an additional guidance signal from the higher level layers to usual back propagation. This prevents backward flow of negative gradients. So it can solve the problem that we just discussed. As we can see here, the noise has already reduced a lot, and it shows the dog face and the cat face. But still, its limitation is that we do not know which part of the image lets the network make the prediction decision. Let's say if we want to know which part of this image make the network to predict the cat part, but the visualization show both dog and cat face, so that will make the things hard. Then next group of people introduce two methods called CAM and grid CAM. In CAM, we first input the image into the convolutional layer, and we get a bunch of feature maps, And after input the feature maps into the global average pooling, we will get the weight of each feature map. And we add the weight to the feature map, we will get the class activation map. This class activation map help us to label the very important region that make the model to recognize the dog. But the limitation of this method is that we need to retrain if the model do not contain global average pooling, because not all of the methods use global average pooling, so we need to retrain and include the global average pooling layer. Then, to solve this problem, a bunch of people include a method called GradeCam. In GradeCam, they say no matter which kind of network or which kind of task you are doing, they can always generate a map similar to what CAM generates. So the theory behind that is they compute the gradient according to the predicted scores, and they will get the weight for each feature map, as we discussed in CAM. So let's see the performance of GradeCam. With GradeCam, we can see that if we want to know which part of the image make the model to predict the cat class, we can see that the region is mainly on the cat region, and if it is the same for the dog. More interestingly, this work combined a guided gradient with the CAM. They find that it actually solved the previous problem that we just discussed. Because in this map, if we want to predict the dog, the visualization of the feature map only show the dog face. It will not include the cat face anymore. But how to utilize the interpretability to develop a good algorithm? A group of people find that the filter of the CNN actually learn mixture of patterns. So as you can see here, the red circle not only crop a kind of class, but it crops like different class together. So that is called mixture of patterns. But that will stop what we learn the CNN inside. So there's a method called explanatory graph. They use explanatory graph to separate the mixture pattern. So now in this way, the mixture patterns are separated, and we can get which part of the image caused the model to predict the right class. Furthermore, they introduce a method called interpretable convolutional neural networks. In this method, it estimates the potential position of the object part of the feature map, and for CNN, it designs a specific mask to filter out noisy activations, and then use loss to push filter to represent a specific part of the object. And this helped the model automatically separate the mixture patterns. And we can see the performance here. If we use the traditional filter, traditional CNN, we will still get the mixture pattern. But if we use the interpretable convolutional neural network, we will get only one single pattern. So that this work used graphic representation to model the CNN in an interpretable way. And they introduce a new algorithm according to this kind of interpretability things. And that's all. Thank you.